Welcome to our class discussion on the graphs of functions, some different characteristics, how we can move our graphs up, down, left, right, how we can flip them over either the x or the y axis. Some of those things we're going to talk about here as we go along. We're going to start out this lesson with defining a couple new characteristics, if you will, for functions, those being the even and the odd functions, and what it takes for a function to be either even or odd. Now, if we look here, we see this definition: f of negative x is equal to f of x. And so we say, well, what does that mean? Well, that just means that here's the function f of x. If we replace x with negative x, we're going to get, in other words, if we replace x with negative x, this would be negative x quantity squared, which is x squared. Alright, and then an odd function, f of negative x, is negative f of x, or the opposite. So the opposite of f of x in this case would be the opposite of x squared. And so we're looking to see, using those definitions, whether or not a function is even or odd. Now, if I know that I have to test to see if the function is even or odd, if we look here, we know that we're going to need to know the value of f of negative x in both situations. So f of negative x in this situation is equal to the absolute value of negative x minus 3. And of course, we know that the absolute value of negative x is equal to the absolute value of positive x. And we can just say that here. Oh, excuse me. About to write a minus sign where we need a plus. So absolute value of x minus 3, that is f of x. And so we can see that since f of negative x equals f of x, then f is even. And one thing about it, if f is even, you'll notice that an even function is symmetric with respect to the y-axis. So we have symmetry with respect to the y-axis. Alright, and if a function's even, it's not going to be odd, so we will move along here. We could go ahead and check it if we wanted to. The opposite of f of x, we can see that's the opposite of the absolute value of x. And then we've got a minus 3 here. Well, this would be the opposite of the absolute value of x plus 3, which is not equal to f of negative x, which is the absolute value of negative x minus 3, which is f of negative x. So f is not odd. So functions that are even or odd, knowing that helps us know something about their graphs. Vice versa, if we know that a graph of a function is symmetric with respect to the y-axis, then we know that it is going to be even. Let's check out example 2 here. First, I'm going to find f of negative x. Now, here we've got 3 times negative x squared plus 2 times negative x minus 4. Well, negative x squared is x squared, so we've got 3x squared minus 2x minus 4. And now we need to look at the opposite of f of x. Well, I'm just going to put a negative in front of f of x here. Alright, so we've got negative 3x squared minus 2x plus 4. Now let's see, we know that if a function is going to be even, then f of x would have to match f of negative x. And we notice that is not the case here. F of x does not match f of negative x, so f is not even. And Let's see here, f of negative x, does that match up with the opposite of f of x? Well, no, it does not. So f is not odd either. You know, I've had students in the past, they say, well, what do I do? The function's not even and it's not odd. How do I show that it's not either one? Well, if it's not even and it's not odd, then you're done, folks. F is neither even nor odd. I'll give you a chance to try a couple of these with discussion problems 6 and 8, and then you can see we've got 3 problems there to work for homework. Well, let's take a look now at graphs of functions. And we know that the graph y equal f of x, it's pretty easy to sketch in the graphs of y equal f of x plus c and y equal f of x minus c. Now, we've defined c to be a positive real number here. So when we add c, we're doing something like a plus 5 or a plus 10, something like that. Over here, f of x minus 5 or f of x minus 10 is what we're looking at. You'll notice that this shifts the graph of f upward by a distance of c, and as long as c is positive, f of x minus c, we subtract c from each y-coordinate, thereby shifting the graph of c downward. We call these vertical shifts. Sometimes we use the word translation, but our book likes to use the word shift here, which is fine. You can see some examples. The blue graph, y equal f of x, and then the pink graph, y equal f of x plus c. You'll notice that we've taken every point on the blue graph and we've raised it up c units. Over here we've done just the opposite. We've got f of x minus c, so we take the blue graph, which is the graph of f of x, and we drop it down c units. So we are asked here in example 1 here, we are asked to sketch the graphs of y or f of x equal the absolute value of x plus c. Now, I'm going to do one thing that they didn't ask us to do here. I'm going to graph f of x equal the absolute value of x, which of course is the absolute value of x plus 0. And so we hopefully are all very comfortable with what this graph looks like. So here we go. Now, the next thing that we're going to do as I switch colors here, let me find a nice shade of blue perhaps, f of x equal the absolute value of x minus 2. What we're going to do is we're going to take each point on the black graph and we are going to shift that down 2 units. So each one of these points I'm just pulling down 2 units, and then it's your good old favorite game of connect the dots. Isn't that exciting? And now we're going to go for f of x equal the absolute value of x plus 1. Let me shift to red here maybe. F of x equal the absolute value of x plus 1. Now, here we're going to take the black graph, we're going to move every point up 1 unit. Every point up 1 unit here. And then finally, as we reach for the green paint color, we will look at the graph of f of x equal the absolute value of x plus 4. So here we're taking our black graph and we are moving all the points on the black graph up 1, 2, 3, 4 units. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Over here, 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. Alright, so again, connecting our dots here, and we can see what happens when we have vertical shifts or vertical translations. Now, I think you're going to find that these vertical shifts or these vertical translations make a lot of sense because, well, like the blue, you see a -2 and just push it down 2 units. You see a +1 and just shift it up 1 unit. And we should mention here that what we're doing is we're running the input variable through the function. The function here is the absolute value. And then in the case of the red, we're going to add 1 to it. And again, so after this goes through the function, it comes out a y value, and you guys might remember that when we add or when we input a function. When we input a variable, value of the variable into our function, in goes an x, out comes a y, and so it hopefully will make sense to you that these numbers here are impacting the y value, thus causing the shift up or down. Now let's switch gears a little bit. This may not be quite so intuitive. As we look here at this paragraph, we can also consider horizontal shifts of graphs. Specifically, if c is greater than 0, consider the graphs y equal f of x and y equal f of x minus c, sketched on the same coordinate plane as we will soon see here. Let's pull this up. Since g of a plus c equals f of a plus c minus c, what we get is f of a. Notice here how these two guys are going to cancel. And it's because I have to subtract c from this number here to get back where we started. And that's why if I have a positive value c and I'm adding to it, we see that the point with the x-coordinate of a on the graph of y equal f of x has the same y-coordinate as the point with the x-coordinate a plus c on the graph, but this implies that the graph of y equal g of x equal f of x minus c can be obtained by shifting the graph to the right a distance of c. So if we have x minus c, and folks, we're always assuming here that c is positive, if I have x minus c, we're going to the right. If I have x plus c, this graph can be obtained by shifting the graph of f to the left, a distance of c units. And we'll notice here in the chart as we look at the blue graph, and we then look at f of x minus c, that actually shifts us to the right c units. And here, if we have f of x plus c, this actually shifts our blue graph to the left c units. And so now we're going to do a very similar thing that we did in our previous example. We're going to start out, as I did before, with my basic graph, f of x equal the absolute value of x. Let me once more plot that particular graph. The absolute value graph's really a nice graph, nice, straightforward, very easy to see what's going on. So here we go. We are now going to grab our blue color again, and we are going to look at f of x minus 2. F of x minus 2, of course that's the absolute value of x minus 2, and so since we have a minus 2 here, this is going to shift each point 2 to the right. So here we go. Okay, 2 to the right. And then we will come in here and we'll grab our red, f of x plus 1. Well, this is the absolute value of x plus 1. You'll remember that this shifts everything 1 unit to the left of where we were just a moment ago. Left 1, left. Here we go. And then finally, we're going to look at, in green here, f of x plus 4, which is the absolute value of x plus 4. This is going to take my black graph and shift it to the left 1, 2, 3, 4 units. And so we can see here kind of what's going to happen with the green graph. Everything gets shifted to the left 4 units. So here we have horizontal shifts before we had vertical shifts. Now, to obtain the graph of y equals c times f of x for some real number c, we say multiply the y coordinates of the points on the graph of y equal f of x by c, which if you think about it, alright, f of x is my y value, and then we're going to multiply that by c. So hopefully that will make sense to you. For example, if y equals 2 times the graph f of x, or 2 times the function f of x rather, we double the y coordinates. Or if y equals 1/2 f of x, we're going to multiply each y coordinate by 1/2. This procedure is referred to as vertically stretching if c is bigger than 1, or vertically compressing if c is between 0 and 1. You're going to find out later what happens if that number in front of the function is negative. But for now, we'll just think that if that number in front of the function is bigger than 1, it will give the graph a vertical stretch. If that number in front of the function has a value between 0 and 1, we say that we are vertically compressing the graph. And you can see that here. You'll notice in the pink, c is greater than 1. Here in the pink on this graph, c is between 0 and 1, and you can see how the pink graph lies very much closer, I should say, to that x-axis. Alright, so here we go. Are we ready to do some stretching and compressing? Sounds like we're going to do some exercises. Oh, well, I guess we are going to do some exercises. How about that? I'll tell you what I'm going to do, folks. As we get ready to graph this, I'm going to make me a table, and I think you'll appreciate the importance of the table here in just a moment as we look at some of these different functions. Now in black, once again, as I've done before here, I'm going to just graph y equal the absolute value of x, and so I'm going to use 5 inputs here: -4, -2, 0, 2, and 4. And I apologize. Hopefully the notes that you've printed off have a C right here and not the number 2. My apologies for that that typo. So here we go. The absolute value of -4 is 4. Absolute value of -2 is 2. Absolute value of 0 is 0. 2 has an absolute value of 2. 4 has an absolute value of 4. So when we get ready to plot this graph, we're going to go to the left 4, 1, 2, 3, 4, and up 1, 2, 3, 4. And then we're going to go -2, 2, 0, 0, 2, 2, and 4, 4. Alright. Now, let's switch gears here. I'll grab the blue next. And we're going to take a look at 2 times the absolute value of x. So here's what we're doing, folks. Absolute value of -4 is 4, times 2 is 8. Absolute value of -2 is 2, times 2 is 4. Absolute value of 0 is 0, times 2 is 0. Can't do much with 0, can we? Absolute value of 2 is 2, times 2, well, that's 4. And the absolute value of 4 is 4, times 2 is 8. So now we've got -4, 8, 5, 6, 7, 8. We've got left 2, up 4, left 2, up 4. 0, 0 is still right there. Right 2, up 4. And then right 4, up 8. And so hopefully you can see that stretching. You can see that stretching there. I've taken the black and I've pulled them both up, and in doing so I've brought the two sides of that, if you will, of that function a little closer to the y-axis. Now let's take a look at y equal 1/2 times the absolute value of x. So here we go. 1/2 times the absolute value of x. The absolute value of -4 is 4 times 1/2 is 2. Absolute value of negative 2 is 2 times a half is 1. Absolute value of 0 is 0 times a half is still 0. Absolute value of 2 is 2 times a half is 1. Absolute value of 4 is 2 times a half is 1. You know what? I messed up. My apologies. Absolute value of 4 is 4 times a half, that's 2. So here we go. Negative 4, 2, negative 2, 1, 0, 0, 2, 1, and 4, 2. Okay, and we can see here the vertical compressing that's going on as we shrink that graph down. And so I'm going to let you guys try what happens when C equals 4 and 1/4 on your own. Of course, you know that the completed set of notes is posted on Angels, so you guys can get on there and check that out. Certainly, and I haven't mentioned this in this lesson, but certainly if you have any questions about any of this, please feel free to bring those up in class. Now we have shifted graphs up, down, left, right, and we've even done some compressing and some shrinking and compressing vertically here. We'll notice that if we have y equal f of x and y equal f of c times x, as long of course as c is not 0, if if x is between a and b, for a less than x or less than or equal to b, are the same as the function values of f of c of x. So what's going on here? You say, well, take a look at this relationship, and then from that relationship, if I multiply my input by c, you can see what's happening with my outputs. I can divide them both, and this implies that the graph of f is horizontally compressed if c is greater than 1, or it's horizontally stretched if c is between 0 and 1. Alright, let's take a minute here though and work one where we've got horizontal stretching or compressing going on. Before we do that, we'll make note here that as a special case, the graph of y equal f of negative x is a reflection of the graph of y equal f of x through the y-axis. So in other words, we're going to have our graph reflected there through the y-axis, and the y-axis would serve as a line of symmetry. So let's check out example 4 here, and we'll just start out with the graph of y equal f of x equal x squared is where we'll start. My input is x once again. Let's go with let's go negative 2, negative 1, 0, 1, and 2 this time. We square negative 2, we get 4. So there we go, negative 2, 4. We square negative 1, we get 1. We square 0, we get 0. We square 1, we get 1. We square 2, we get 4. So here's our old friend, the basic parabola, y equal x squared. And didn't mean to not fill in my table here. Now, let's think about what's going on. Let me switch gears here. We'll go and we'll grab the blue ink. Now I'm going to let c equal 2. So this means I'm looking at 2x quantity squared. 2 times negative 2 is negative 4. We square that, we get 16. So we're way up here. Now we have negative 1 times 2 is negative 2. Square that, we get 4. So we pulled this up here. Of course, 0 times 2 is still 0. Square that, we still have 0. And then by our symmetry, we know that if we put in 1 times 2, that's 2. Square that. And same thing up here. So you can see we are taking a value of c that is greater than 1, and you can see the horizontal compression going on. these hands, if you will, these sides of this parabola are getting closer and closer to that x-axis. Now let's take and see what's going to happen when we fill in 1/2. So here we go. C equals 1/2. This is 1/2 x quantity squared. Now, half of -2 is -1. We square -1, we get 1. So -2, 1. Then we take 1/2 of -1. Well, that's just a half. And we square that, and 1/2 squared is a quarter. So this guy is getting kind of tiny here. Then, of course, 1/2 times 0 is just 0. We square that. And then by symmetry, when x is 1, my output is 1/4. And then when x is 2, my output is 1. So you can see here how, when it comes to horizontally, how this gets a little wider, or a horizontal stretch, we say. And now let's take a look at a case here where we've got a little bit of everything going on. We're going to have a horizontal shift, and then we are going to have a vertical compression, and then this negative out front, if you remember, that's going to reflect things over the over the x-axis. So here we go. Let's bring our black ink back here, and we will first start out with C equal 0. Now, we weren't given an axis here. That's okay. We need to practice drawing this out a little bit anyway. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. Alrighty. So we know what the graph of y equal x squared looks like. That's kind of our little thinking bubble. That's what's going on in our minds. Now, the only thing about this graph is we are going to take all of our input values, and we are going to use them for a horizontal shift here, and then we're going to multiply the output by -1/2. So let's make a chart here just for a moment. Let's go with inputs of we'll start with -1, 0, and 1, and we're looking here at -1/2 times x minus c quantity squared, and I'm going to let c equal 0 for this first one. So let's see, -1 squared is 1 times -1/2. Well, that gives me -1/2. 0 is going to be my next input value. 0 minus 0 is 0. Of course, we square that, we get 0, and we multiply by -1/2, we get 0. And then we put 1 minus 0 in here. 1 squared, of course, is 1 times -1/2. So we've got something that looks similar to this. You'll notice the vertex, well, we haven't talked about the vertex yet in this class, but we will soon enough in the next session. And so you notice here our vertex is at the origin. We don't move to the right or to the left. You'll notice that the graph has been reflected over the x-axis, and you'll notice that we have a vertical compression there. Now let's take a look at, as we go for another color here, let's take a look at -1/2 x minus c quantity squared. This time c is going to be -3. And guys, we know now that we can take this graph we just drew, and we can move everything. Since this is a -3, this is actually going to be x minus a -3 quantity squared. which is going to be negative 1/2 times x plus 3 quantity squared. So that's going to take us to the left 3 units. So same graph, 1, 2, 3 over here. And there we go. So that's with c equal negative 3. And then finally, we've got c equal 4. So negative 1/2 x minus c quantity squared. So this is negative 1/2 times x minus 4 quantity squared. This is going to take our black graph and shift it to the right 4 units. And folks, as long as I don't provide a grid here, I'm okay if your graphs are not quite to scale. Obviously mine aren't either. As long as we've got kind of a ballpark, if I want an exact, I'll provide you with a grid to draw on, and then please pay incredibly close attention to detail as you sketch it in on the grid. If you'd take a look at problems 18 and 22 now, to work those for class discussion, that would be good. And then you see a list of problems you can do for homework there. And as we move along, we're going to now look at example 6 here in our notes, which is problem 28 from the set. Instead of actually graphing these, we are going to describe what's going on with the point. We're going to describe what's going on with the point. And so notice here our point is 3, negative 1. This is 3 f of 3, if you will, okay? And so f of x here, f of x in our case equals 3. And so we're going to pardon me, f of x, my y value, equals negative 1. My apologies here. Make sure we fix this. So we are going to start out, the first thing that's going to happen, we are going to multiply negative 1 by 2. So this leaves me with the point 3, negative 2. We haven't moved horizontally yet, just up or down. And then the next thing that you'll notice is we're going to add 4 to the y coordinate. Alright, and that's coming from this guy right here. So this is going to give me 3, 2. This is going to give me 3, 2. Alright, so I think it's helpful to go ahead and write these points with each step along the way, just so that you can kind of keep track of where you are. We'll give you an opportunity to try this with 28 and 32, and then for homework you can work 27 and 30. Now if we look at example 7 here, this is problem 34 from our textbook. It says explain how the graph of the function compares to the graph of y equal f of x. For example, the equation y equal 2 times the quantity f of x plus 3, the graph is shifted to the left 3 units and stretched vertically by a factor of 2. Here we can say that f is shifted. Now notice this is a minus 1, so we're going to shift right 1 unit, and then we are going to be stretched, so and stretched vertically by a factor of 3. And if we look at problem number 40 here, no shifting going on. We are just compressing f of x by a factor of 1/3. And we even might say we are vertically compressing f of x, and we know we're doing that because we're running our input through the function first and then we are multiplying that by a factor of 1/3. And so finally, as we get ready to wrap this up, you can see the discussion questions there and then the homework questions. As we get ready to wrap this up, we are going to take a look here at our last couple examples. What they want us to do is graph each of these described in A, C, E, G, and I. I've just selected a few of these here. They've given us our basic graph, if you will, and they want us to graph accordingly. So here for part A, we'll see that this is f of x plus 3. We know that this is going to take our graph that we're given and shift everything to the left 3 units. And so we'll sketch in our vertex here. To the left we go. Alright. And then if we look at the next one is for part C, y equal f of x plus 3. This is going to take our graph that we're given and shift everything up 3 units. And on something like this, guys, if you'll just kind of get the vertex, get the main point, if you will, about right, that'll be good. Do your best approximation, but as you've noticed, I'm no artist, and so I don't expect you to have a degree in art either. Now, we're going to take a look at part E, and you'll notice what's happening. We've got a vertical stretch. Let me write this out here. Vertical stretch by a factor of 3, and then reflected over the x-axis. That's what the negative does for us. So as we get ready to look at E, we know we're going to stretch this thing up a little bit, but we've got to make the reflection. Alright, so yes, we have a vertical stretch, but as soon as we stretch it up, it's going to flip right over that x-axis. Now if we look at our next graph, you'll notice that we have here a horizontal stretch, if you will, and so we're going to flatten things out, but this is going to, the negative inside of here, this is going to reflect the graph over the y-axis. Now we know that we've got a graph that's symmetric here anyway, so it's not too big of a deal. And so what you'll notice here is we look at the graph of G, is we're going to have to flip this thing over here, and we've got a horizontal stretch, if you will, by a factor of 1/2. So that's what the reflection about the y does, and then we've got the horizontal stretch. And then finally, the last one has quite a bit going on here. Let's take just a moment and detail it. When we look at part I, we're going to go left 2 units, reflect through the x-axis, and then down 3 units. So number 1, continue our order of operations, working kind of inside out, that we learned this order of operations we learned way back early in our algebra days. We're going to go left 2 units, reflect over the x, and then shift down 3 units. So here we go. We're going to move this bad boy left 2 units. We're going to reflect it, and then we're going to move down 1, 2, 3. And so it didn't quite allow for enough hash marks here, but we'll continue on with that. And I've put in an extra grid here in case you want to practice or whatever. For class discussion, please take a look at problem 44. You'll notice that I was nice and saved a few of the problems on 41 and 43 and 46 for you to work in the homework. Again, just kind of label where the main part of your graph is and give a pretty good ballpark estimate of it. That'll be fine. That'll be fine. Now, we get ready to look at another type of function. We mentioned this a little bit when we studied the absolute value functions back in the first unit. Let me remind you, I talked at one point about how the absolute value of x is equal to x if x is greater than or equal to 0, and it's equal to the opposite of x if x is less than 0. And I may have even used the term piecewise defined function. This is a piecewise defined function because, well, how it's defined is broken up into pieces, quite simply. The absolute value of x is equal to the input part of the time. It's equal to the opposite of the input the other part of the time. And hopefully, as we study some of these, it might help you with some of those problems from section 1.1 where we were asked to replace absolute value notation with other types of notation here. Do we need exactly what's inside the absolute value bars, or do we need the opposite of what's inside the absolute value bars? Now, let's take a minute here and look at example 10 as we get ready to do this. What I'm going to do is I'm going to sketch in for us all three of these functions. So I'm going to put the top one in blue. Now we know what y equal negative 2x looks like. We've got the point 0, 0. X equal 1, y is negative 2. X equal 2, y is negative 4. Likewise, x equal negative 1, y is 2. X equal negative 2, y is 4. Alright, so we know that this is a line. And let's see, what did I do? I got off one there. Let me correct that. My apologies. So negative 1 or negative 2 up 4. So there's the top piece of this function in blue. And now let's take a look at our second piece. We'll do it in red. Y equal x squared. We know we've got 0, 0, 1, 1, 2, 4, negative 2, 4. Oh my goodness. I see that I still did not quite get that point in the correct spot there on the blue, did I? Let's see if we can get that here. My apologies. Alright, so there's the blue. Okay, now back to the red. Negative 2, 4. We know when x is negative 1, y is 2. And it would help if I could put the points in the correct spot. There we go. One, 2, and then 2, 4. Alrighty, we're going to get this here. So here's our friend, the parabola. Oh my goodness. This is the square function, isn't it? I apologize, folks. Let's revisit the red here just momentarily. Let's try this red one out here one more time. So we've got this, and then 1, 2, alright. So here's our linear function. Let's do the red one more time. See if we can get the hand and the brain and the mouth to all say the same thing. If x is 0, 0 squared is 0. If x is negative 1, negative 1 squared is 1. If x is negative 2, negative 2 squared is 4. So there we go, 1, 2, 3, 4. If x is 1, 1 squared is 1. If x is 2, 2 squared is 4. Oh yes, looking much better now. And finally, we get our friend the parabola to show up. Wonderful. And then finally, here at the end, let's bring the green into play. Y equal -2. Well, we know what the line y equal -2 looks like. It's this guy. So one way to graph these piecewise defined functions is to draw each piece first, and then what I'm going to do, alright, what I'm going to do, I'm going to get a highlighter here, and you'll notice that from -∞ to -1, we're going to ride the blue line, if you will. Okay. There we go. And maybe the highlighter was not such a good idea, so let me make a yellow pen here. Microsoft Word didn't seem to appreciate that. So here we go. From -∞ to x equal -1, we're writing the blue line. So here we are at x equal -1. And then from -1 to 1, you'll notice that we get on the red line. So we get to fill in our circle here. And then at x equal 1, well, you notice at x equal 1, this other green line takes over. Now, we're going to have a gap in our graph. Try saying that 5 times fast. A gap in our graph. So the graph of f of x is what I've done in yellow. Alright? And so you can see that this is not what we call a continuous graph. Some piecewise defined functions are continuous functions. Others are not. And we can have a little bit of both. Your final answer, if you were to turn this in for homework, would be the yellow graph. Now, some people are very good about being able to look at the problem and just use, in this case, the yellow pen to draw in the graph of f, and they don't need the blue and the red and the green to help them out. But I think, especially at first, it's very, very helpful if we can draw in each of the parts, and then with an extra color we can connect them all together so that we can see what the graph of f really looks like.